or something because it'll be these slides, but this is the special Soul edition. So you'll get my take on it. I changed a few of the slides. So we're going to talk about what is Coda, how does Coda work, this Genesis token program, and we're going to have a testnet demo that was going to be a live demo, but there's no computer in front of me, so you'll see. Okay, so Coda, the big thing is we use a zero-knowledge proof to stand in for the blockchain. So rather than having every node on the network have a copy of every block that gets produced, no one has to store anything. And this gives us better decentralization and usability. So I'll talk about that. Decentralization first. Right, cryptocurrencies are traditionally backed by blockchains. There's a blockchain, and we want everyone to have access to the cryptocurrency protocol. But the problem is, as transactions flow through the network, blockchains grow, and once the chain gets too large, it becomes hard to have a computer with enough hard drive space, let's say, to even store the blockchain. So, and then you have to depend on full nodes, and you have to delegate trust. And in that case, like, do we even have a decentralized network anymore? So here's some data. Sorry, I landed this morning at 5 a.m., so I'm quite tired. So sorry. Bear with me. So you can see the Bitcoin nodes, that's the blue line at the bottom, that's stayed relatively stable over time. But it hasn't grown, even though, despite Bitcoin becoming more and more popular. Or, I guess you could argue, but there's a clear trend line for the Ethereum full nodes over time, right? It's going down. And the Ethereum blockchain is also growing a lot faster than Bitcoin. So, maybe the blockchain size is one of the factors here. So this is not a good thing, because it means that these cryptocurrencies are becoming more centralized. Okay, so let's fix that. There's two things we can do. We can make the blockchain small using zero-knowledge proofs, and we can use a consensus protocol that is inclusive. And I'll talk about both of these things. So, the zero-knowledge proof bit. Sorry. I'm lost. Anyway, these are the two things. We are going to go into detail, but not at the next slide, okay? This is the preview. Right, usability. So it needs to be easier. Cryptocurrencies are hard to use. And I think, this is one of the reasons why it hasn't become more popular in society. The folks here are into it, but actually most of South Korea is ahead of the curve. But in America, if you walked around, people aren't into cryptocurrency as much. So why is this? There's a lot of reasons, but one issue, if you want to get a traditional user of an application interacting with the blockchain in a fully decentralized way, they need to download 100 gigabytes of data. So that's not good. But with zero-knowledge proof, then everyone can have full node security. Everyone can verify the state of the world in seconds in browsers and phones. For nodes participating in consensus, minutes, and you don't have to download all transactions that have ever happened over time. And then in the future, we want to use zero-knowledge proofs to help this. These large corporations, they have a lot of data, and they're using their supercomputers to compute things, and they're coming up with answers. This is very vague, but hopefully someone's following me here. We get information, and why do we trust that this is right? Why do we trust that these computers ran this code that they said they did? We shouldn't have to. And I think, Coda can be used as a substrate for enabling proof certificates that the computation that we think is running is actually running. Okay, now we're gonna dig into the details. Sorry. So let's talk about SNARKs for a little bit on SNARKs. So first, just regular programs on computers. You can model them like this. It's, let's say, a function. We have some amount of inputs, argument 1, argument 2, etc. That big square in the middle is a function that's doing something on those arguments to produce an output, and we produce an output. So maybe we take two numbers and we add them together. Or maybe we take a lot of numbers and we do some interesting financial analysis on it. Right? Cool. Programs. Okay. So SNARKs. So the thing on the left is our first regular program that is normal code. The other two columns, the middle and the last one, are these programs that are created for you when you want to use SNARKs. So there's a way to transform a program that you've written over here into these other two. So the middle one, we call the prover. It takes as input all the inputs in the original program and the source code of the original program. You have to tweak it a little bit, but metaphorically, the original source code of the program, and the output of if you ran that program on those inputs. It takes all those things as input. And what it does is it produces this SNARK proof, this certificate. It's about, it's less than a kilobyte in size. And this certificate can only be created if f applied to those inputs equals that output. And if it doesn't, then it cannot be created. And this is because of some crazy, awesome cryptography that we're not going to talk about. But you can ask your resident zkSNARK expert about it. So then the verifier, the second part, it takes as input the original program, all of the original inputs, the original output, this certificate that the prover generated, and what it does is it just returns true if f on the inputs is the output. If the certificate was truly created by the prover, and if it wasn't, it returns false. And the cool thing is that the verifier runs very, very fast, essentially constant time with respect to everything, honestly. Concretely, it means hundreds of milliseconds on a decent computer, seconds on slower hardware. So here's how we use it in Coda. In a very rough, general sense of that, in one sentence, our program takes a block, the next block in the blockchain, a proof, one of these SNARK certificates that says all the blocks from 0 to now, like until the block before this new block, is valid. So it takes a proof of that. And this f, this part, says that the proof verifies, so like everything up to now is good, and the next block is a valid successor to the blockchain that did exist at one point, but we just have a proof for. And then we make a proof of that, and that gives us a proof from 0 to this new block. And we do that again and again and again and again, and every time we get something less than a kilobyte, but we're always extending the blockchain one greater. So that's that. And the cool thing is everyone is a first-class user. There's no need to depend on anyone for access to a full node. You don't have to delegate trust at all. So this is great. You get easy, permissionless verification. Awesome. Okay. Let's talk about consensus a little bit. So I don't know how I'm doing on time. I don't have a clock, but hopefully it's 17 minutes. 17 minutes long. Cool. Okay. So we use Ouroboros. Before I even go over that, though, I'm just going to talk about proof of stake a little bit. I know this whole conference was about proof of stake, but let's just make sure we're on the same page. Here's how I think about proof of stake. I think, so we can draw a circle, and inside the circle is all of the tokens in our protocol, okay? And then what we're going to do is we're going to cut slices of pie, or Korean pizza, or whatever, some circular food, bibimbap, and you don't do that bibimbap, but and each slice is the amount of tokens that one account has. So like in this case, the blue account has a lot of tokens, So here in our network, there's 4 accounts. Blue and green have a lot of tokens. Purple and red have a decent size. Okay, and then proof of stake is this process of you throw a dart. You have darts in yeah. Okay, so you throw a dart and the dart uniformly at random lands somewhere inside the circle. And if it lands in the blue area, then the blue account has permission to create a block. So proof of stake is about making this process happen where every node in the network agrees on the dart landing in the same spot in a way that no one can influence it to do something bad. So here's Ouroboros. So okay, here's how the Ouroboros proof of stake algorithm throws the dart at the pie. Okay, time is divided into slots. Slots on our testnet right now, they're 3 minutes, but we're going to get it down before mainnet. But you can think in each one of these 3-minute slots, we're deciding where another dart to throw. The idea is we have to make the network agree on the randomness of where the dart's going to land in such a way that no one can influence it. So how does Ouroboros do that? We take the slots, these 3-minute chunks, we then group them into groups of k, which is just a constant that in this diagram is set to 1,000. In our testnet, it's 10 right now. Groups of k, okay? And then we group those k things into 8 chunks. And we group those 8k things 3 times into an epoch. The only reason I'm going through this grouping is because we use this nomenclature everywhere, so maybe you'll see it and you'll have a better understanding of what it is. But the point is, we group these slots together, and there's this invariant in the Ouroboros algorithm where an adversary, an evil party, as long as they don't control the majority of the stake, they have essentially no chance of creating a fork that's longer than an epoch in a row. So essentially, this means that if you look at an epoch of blocks, it cannot be a fork. It has to be on the main chain. And so what we do is we then take that epoch worth of blocks and use that as the seed for our randomness for the next dart throw. And then adversaries can't influence it. There you go. Hopefully that makes some sense. Okay. And yeah, the cool thing is, well, I guess I didn't talk about this yet, but the process of actually throwing the dart, it's something that you do on your own computer with your own private keys, and you don't have to communicate to the network unless you won. And so everyone throws the dart by themselves. They don't talk over the internet about it. And the one person that wins, or just think of it like that, the one person that wins is the only network traffic that says like, okay, here's the block. Because of that, essentially the number of participants in consensus is unlimited because you only communicate when you win, which is nice. So it's inclusive. It's great. Economics. All right. Coda will have 1 billion tokens at launch. We will break this into 1 billion pieces each. So there's nano Codas is like a Satoshi token. There will be 12% inflation at launch, which goes down to 7%. But this inflation is not like inflation in state currencies. It's inclusive inflation. That's what we like to call it. If you are delegating or staking, the 12% inflation goes back to your account as rewards. Then there's also this thing that's special on our network that really deserves more than 2 bullet points, but we don't have time, called the SNARKs. And I'll talk about this more at the Coda meetup tomorrow. But we have this extra type of node called a snark worker, whose job is to just compute snarks of transactions. And then block producers, the people who win the dart throws, they have to buy these snark transactions from snark workers in order to accept transactions from the transaction pool. And they earn the difference between it. So Luke was talking about in an earlier talk, if you're like good at game theory or economics, you can be better than people and have an economic advantage. Our network is an example of that. Cool. So, Genesis program. We have recently announced a program where we will distribute 66,000 tokens. 1,000 members will be selected. So this means that 6.6% of the protocol will be distributed, which is way more than other protocols, as Luke said. So we're really excited about that. And that's a lot. So this can hopefully offset that cost that we learned about in the State Fish Talk about, you have to make a lot to sort of make validating profitable, but if you get this grant, it'll help. So, yes. By the way, it's equivalent to 187 2080 Ti's mining on Ethereum to get that much stake. So that's a lot. You can learn more terms and conditions. Codaprotocol.com/Genesis here. And there's these buttons you can apply and join our Discord. And then press the participate in testnet button. And currently, the actual node operation in our testnet, our rewards for that are on hold until at least an announcement February 14th for interesting reasons that we can talk about. But we basically found this awesome issue when we had hundreds of people join, or 150 nodes at once join. So we want to fix that before we ask more people to join. But there's plenty of stuff that you can also do to participate and win. So that's it. Let's go to the video. How much time do we have? 10 minutes, great. So okay, this was going to be a live demo, and the testnet is alive for me to do a live demo. Just want to make that clear. But I would have to stand over there, and I'd rather you see me. So, so luckily we have a video of almost exactly what I was going to show. So I'm just going to talk over the video, and hopefully it goes quite a little fast, so I'll just have to talk fast. So this is a video that our reliability engineer Connor made. It's about running Coda in Google Cloud. So Google offers a $300 free credit where you don't even have to apply as a startup. You can also get 50,000 or 100,000 if you do that. But $300, all you have to do is hit a blue button. So with that, here's how you get started with a Coda node. So you go to Google Cloud Platform, you make an account, Compute Engine, VM instances. Okay, now you make an account. You go through this, $300 credit. Cool. Pretend I'm typing. Okay, so now we create a new VM instance, name it something. You'd set your region to Seoul instead of Oregon. The instance type that works well for Coda is around like 4 CPUs and 16 gigs of RAM. 8 gigs of RAM should work too. You'll want Ubuntu. We support a recent version of Debian also, but 1804 Ubuntu and 25 gigs of disk. And then we need to open ports so that people can connect to us. So that's in this section here. Well, in this section, we make a tag, and then we refer to that tag in another section. So I'll post the link to this video somewhere, so you'll be able to follow along. But, you can also add your SSH keys, but you don't have to. Google Cloud has a online console to make it even easier. Hit create. You need to wait a little bit, but eventually it's like 1 minute, and then this will come up. But in the meantime, you can go to the menu again, VPC network, firewall rules. Now we're going to open ports so that nodes can connect to us. We make a new name for firewall rule. We have to press ingress. This is like incoming traffic. This is the tag that we made in the other screen. And then here it's what IP addresses do we want to allow to talk to us, all of them, because this is a peer-to-peer network and we want to connect to everyone in the world. We want to open those ports, 8302 and 8303 on both. These are the default ports for communication in the GossipNet and other point-to-point communications. And then by now your VM instance will be open. You can press that SSH button there, and a terminal will pop up in your web browser. And it'll take like a minute or so to load. But in the meantime, you can fast forward the video, or you can just, and then you go to docs getting started, and then there's instructions here on how to download for Ubuntu. As Luke showed on the earlier talk, we support Mac OS as well, though in South Korea no one uses Mac, so I don't know, as far as I can tell. But all of you have web browsers. Then you let it install, and you go to the next page of docs, and you have Coda. My first transaction. And then you just paste this line, and we always keep this up to date. And you're done. And you have a node. It's in the cloud, $300 of free credit, which should last a couple months. And you're connected. And then there's a few other commands to actually stake and such, but this gets you in. So yeah, that's how you do it. Yes. So this will work today. What won't work today is please join our Discord server. Okay. Let's look at some EC2 windows and then some Thai. Yeah, you can close it. Can you go back to the slides? There's just one more slide. Although it's not even important. Because it also probably says, no, it is important. It has so many important things on it. Join the Discord here. Follow our progress on Twitter there. The link is unreadable, but it's codaprotocol.com. And the Genesis program is codaprotocol.com/Genesis. And you should join that now. As I was saying, the testnet right now, there's a 50% chance that when you join it, you'll sync to a bad fork and not the correct tip. So we want to fix that bug before we funnel lots of more people into it. But feel free to try it. And that, how am I on time? Look at that. Hopefully I wasn't speaking English too fast. I apologize. But anyway, thank you, thank you, Nance, for letting us host this event with Steakfish, and it's awesome. Your space is awesome. Everything's great.
혹시 질문 있으실까요? 없으시면은 다음 순서로 넘어가겠습니다. 다음 세션은 테소스 측에서